Let's continue to talk about solar forecasting techniques. This video clip will give an overall concept of machine learning algorithms, statistical model, neural network model that become fundamental techniques to develop forecasting model. The first one is a statistical technique, linear regression, and it is a simple model. It says that you have the predictors, n predictors, x1 dot 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 xn, and the relationship to the output is linear. So your job is to determine these regression coefficients, beta k, so that your y hat is best fit with the y in the least square sense. So when y hat minus y measured by the two norm is at minimum. That's what it means by linear regression. Um, we have some example that when the response variable, when y is irradiance, you can use the predictors as the lag irradiance with the weather variable. On the other hand, if you want to forecast the power directly as the response, your predictor, your xk can be the lag power, the lag irradiance, and the weather variable. So in the past literature, this become very basic, and so it's extended to the framework where the coefficients beta k can be adaptive. Uh, so this is called model output statistic in atmospheric science. And so basically it relies on the principle of applying the Kalman filter. Kalman filter so that these beta k can be time varying coefficients as you have new data arrives. So the set of predictors can be chosen by statistical technique called stepwise regression. So in this example, we give the graph of the PV conversion model. So this model convert the irradiance to the solar power. So we apply this linear regression technique because we see such a clear linear relationship between solar irradiance and power. So I mean, uh, I mean, in the mathematical detail, these can be solved very efficiently. It becomes a very useful technique that appears that available in any software. Next, feed-forward neural network. Now we give just a fundamental concept. So a fully connected feed-forward neural network has three components. So first one is the input layer. So it has in this example, three nodes or n node. It depends on your dimension of the input or your x. Okay. It has hidden layers that contains just a number of neurons as well, and you can have many hidden layers. Okay, so the transformation from one layer to another layer is going to be F5 transformation. So you can think of this as the weight times the input X plus some bias. This is called F5. The third component is the output layers. The number of neuron in the output will depends on your target size, depends on your Y. If your Y has is scalar, there's one neuron in the output layers. In our application, I'll let you think. As I said before, in our solar forecasting or any forecasting problem, you typically have uh, multi-step forecast as the target. So it means that the number of neurons in the output would be H. Okay, so it's a vector, it's a target vector, or the multi-step output. Hmm. Oh, I forgot to mention that in the neurons in the hidden layers, there's a nonlinear activation function that creates nonlinear dynamics in the neural network. So typical activation functions are the hyperbolic tan, the s- the 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 sigmoid function, the ReLU function, and many more. There are many recently proposed new technique as well. Um, the the transformation here to the output layer are just affine. So the model parameters of ANN are just weight and bias terms in all the layers. Mhm. So typically ANN can be used for both classification and regression. So here our problem is the regression task. And when you apply these two tasks differs by the choice of loss function. So if you want to use NN in the regression task, in the forecasting task, make sure you pick the right loss function. Uh, as I mentioned before, common loss would be MSE, MAE, and other available robust regression task. When you fit neural network, you have to pick an appropriate network architecture. For example, how many hidden layers, how many neurons, and as I mentioned before, this thing is called hyperparameter. So you can tune it on the validation data set, or you can start. And I mean, when you try to like develop a model, construct a model, try to start with a simple one first and see whether the loss function can be improved by using a more complex architecture. Mm. When you apply these neural network or in um in model itself is a static model, but you can define an appropriate input output mapping so that the NN itself can behave like a dynamical model. Um, and please keep in mind that the capacity that gained by adding the new unit or the neurons, all right? So adding more neurons and adding more hidden layers, okay, make your model more complex. But usually adding the new hidden layers can improve the model capacity more than adding the neurons. Okay. As I mentioned before, when you apply NN, make sure to pick the cost objective based on your preference. L1 loss is equivalent to MAE. For L2 loss is equivalent to MSE, mean square error. When you train the neural network, um, usually the weight and the bias or the model parameter are randomized as initialization. And when you apply, you have to choose algorithm parameter. You choose the optimizer, that is the algorithm choice, and you may apply. I have some example. You apply the mini batch optimization, stochastic gradient, um, and so you also need to define your stopping criterion as well. Um, there will be terms about when you apply the mini batch optimization, there will be terms on the batch size. So basically, in short, it means that if your data is suppose your whole data is this training data, you're gonna split them into mini batches that defined by the batch size. And you're gonna train the model, but when the model is trained, the model parameter is adjusted based on each batch data set, like in one iteration, and then you're gonna uh, continuously perform in sequence until you use all the batches. That's that makes one epoch. All right. When you use the whole data set one time, that is one epoch. And then you're going to repeat again. You're going to repeat again to the second epoch and so on. Okay. Um, so this is some example of applying ANN to forecast the solar power directly based on this configuration. All right. So suppose I want to perform 8 steps of the solar power, then the number 8 would be the number of output neurons. All right. So the number 8 would be here, 8 neurons. And if I define the input this way, I use the current irradiance, I use the trend that I can compute for the future time. This is exponential moving average. These are example of future regressors. These are the variable that has the value at the future time, but it can be computed at time t. Okay, it's according to this formula. Okay, so you can see some example here. IMA at time t, you're gonna use the measurement. So with this notation, this is day minus 1. So you use the measurement at day minus 1, which is feasible at the current time. Suppose you're at the current day at time t. So this is already available because this is from the previous day. So this is the IMA from the from the previous 2 days. Okay. So you use the past solar power, you use the ambient temperature. You define 3 hidden layer, 128 neuron, for example. uh, uh, so this is, as I said, that we're gonna see the code and the training process in the next video. Okay. Next, um, NN itself is a static model, but as I said, you can, if you put, suppose this is your your yt, right? You can put yt minus 1, yt minus 2, yt minus 3 as the input. This is called auto-lag regressors. Once you apply that in NN, even though NN is a static model, but it reads the information as uh, the output depends on the past input. So now NN plays a role of dynamical model for you. Okay. So there has been a new invention in the past in around 20 something 2016 2015 that for the data that have long range dependence on the time series, uh, recurrent neural network was introduced, and LSTM is one kind of them. So long short-term memory. So the model architecture that I'm going to show the model description here. In short, I'm going to say I would like to explain that the model output will be a temporal dynamics. I mean, the relationship between this guy and this guy are uh, basically state space equation. So this depends on its own past value, or the relationship has temporal dynamics. So it has the element, first of all, x is the input that has the length of RD. The variable h is called the hidden state or the latent variable. Okay. So so it has the dimension h that will be specified by the user. For f is called forget gate. It has a value in the range between 0 and 1. This is between -1 and 1. And the input gate here is in the range of 0 and 1 because it's the output of the sigmoid function. Okay. So the forget gate is to determine whether you're gonna have the information flow or the information that through here should be forgotten. All right. So that's why the range of f is between 0 and 1. So the input of all these guys, O is called the output gate. C is the cell memory, is in a vector of RH, and you also have the the C tilde, which is here. Okay, so all of these three guys take the variable x as an input, And make I want you to make and know you to notice that there's a delay step from the latent variable or the hidden state that uh, it has a delay step here. So it means that it used the past information as the input of these variables. So in short, if we try to explain by the mathematical description, the forget gate depends on x, your input at time t, and the hidden state at time t minus one. That that constructs that construct a dynamical equation. All right. Things also apply the same way. The input state contains the past information of the cell as well as the O. So, and you can see here that there are a lot of composite function. First, these are F5 transformation, and now you have nonlinear activation here. Uh, so this is the element-wise multiplication. So you can see that these cell state as the memory cell state as well is governed by dynamical equation because it requires its own path as the input. So at last, you will see that the hidden state ht depends on O, but O depends on st minus one. So O depends on st minus one, right? So and also as well, ct depends on ct minus one. That depends on the path of h. So basically, there's a very complicated nonlinear function here. Not only that it's nonlinear, but your HT depends on nonlinear mapping of its own past. So for this mechanism, that's why the LSTM was introduced to explain the temporal dynamic of time series. So the output of this is called like the whole thing. This is called LSTM cell. When you construct a model, you can patch this with another layer, another linear layer, or another dense network, or you would like to patch with another LSTM cell as well. I will explain shortly. Uh, the output of LSTM is the hidden state, is H. Um, when you patch the data X to the LSTM, uh, I mean, because you want LSTM to learn the dynamics of your target variable y, right? So typically your input vector x should contain the autolag of y and the exogenous variable. Okay. um when you apply LSTM in solar forecasting, I think now this is the role of any researcher or the any analyst to come up with an idea to propose the architecture. So I have some example of our research team. So these are simple ideas. Um, First one is just classical LSTM cell, but I use the multiply by L. It means that I have LSTM cell patched in cascades, and I put the last linear network, the linear layer, to release the output. And that output I define as the the edge forecast steps. For the input sequence of LSTM, the input structure of LSTM typically is a 2D. I mean, this is for one segment or one sample of LSTM input. This is a 2D array. So on this axis, this mean the first variable, the second variable. For example, this is the variable y itself. uh suppose your y is the irradiance, right? So On this axis, you're gonna fill many variable as you want. So suppose this is I, you may include the cloud index, you may include the temperature, and so on. On this axis, you will include the lag values of this. So this is so the first one is the auto lag of your target variable is a must. All right. If your target is I, you must include the auto lag of I. Okay. And because by preparing the input sequence in the 2D array in this way, it implicitly requires that the order P lag of the auto lag and the exogenous lag must be the same. That's limited by the LSTM data arrangement. But in principle, the lag order of exogenous variable and the lag order of the target itself don't have to be the same. Mhm. If you use other learning algorithm like the tree-based algorithm, you can choose the both lag order to be different. So this is one typical classical way to implement LSTM for multi-step forecasting. The second one, okay, the second architecture relies on the assumption that I have the future regressors. Not only that, I have the exogenous lags. So because the future regressor directly explain the target at the future time, right? So in this idea, I have L cells of LSTM unit, right? So I'm gonna use the output of LSTM, and I'm gonna augment these variable with the future regressor. I'm gonna concat them and put them into a dense network that release the output of the edge steps forecast. Okay, so again, it allows you to pick the number of hidden layers here. You can still choose the number of cells that is appropriate. So if you pick this category, if you pick this architecture, the effects of ZT plus one, right? I mean, in our assumption, ZT plus one, the future regressor, should highly correlated with Y hat T plus one, right? I mean, the time should be correspondence. For example, this is if this is the I hat, right? This is I hat at 10:30 and so on, right? And for example, the future is the weather forecast of irradiance, or I use the term NWP. This is the weather forecast of irradiance from another numerical weather forecast service. Mhm. Then my I had my I had NWP at 10 a.m. would correlated highly with my I at 10 a.m., but not at 10:30, right? So, but when you concat all the regressor in this way, right? You kind of use all the future regressor at different times. You fuse them into a long, right? A long new input to the dense network. That might not be a good idea. So that's because I mean the effect of ZT plus one shouldn't have impact much on the output at other time steps, right? But when you put all of them in the dense network like this, the impact are fused. So that's why we also propose the third architecture where we still have LSTMs, right? And then we concat. Now we're gonna do things in parallel. So the output of LSTM will be concat by ZT plus one dot 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 ZT plus H, and each of the concatenated uh, output would go directly to a dense network, and there are edge dense networks here. Each of the dense network is responsible for each k-step of the output. So you would see that this architecture create uh, many dense network as submodels. Each of the submodels try to use the information from the LSTM that you're supposed to learn temporal dynamics of Y, right? But it applied a more direct impact on the future regressor at each at each uh, at each target time. Mhm. Examples of the future regressors are clear sky irradiance or the weather forecast, things that you can compute for the future times. Mhm. Um, okay, so this is an example of LSTM. When we explain the coding, we will come back to this diagram again because when you implement the code, you should, I mean, the very first thing is that you should have the model diagram of the architecture you want to construct. Next one is also a kind of neural network. This is NeuralProphet. It's a model that become very popular for time series forecasting because it's very easy to use. Um, all you need to do is just to arrange the data set and you just customize only a few parameters. So it has a very meaningful components. It relies on the assumption that your Y can be decomposed into different modules. Let's start with the first one. So suppose your YT is a time series, right, that fluctuates. So it's assumed that your YT here, first it contains a trend. I can also draw another example. Suppose my time series is like this, right? First, it seems like to have a trend that's governed by TT, right? So this is a linear function as of t, but the coefficients here as appears to be a time varying coefficient. So we can basically say that this is a piecewise linear function. So like this. All right, this is trend. The second term is a seasonal. This is a sum of Fourier's term, sine and cosine. So for example, you may notice something like a circle here, right? So that's the seasonal component. In our solar application, the solar irradiance has a daily cycle. Mm. Um, the third one is the event occurrence. In uh the event, right? So because in other applications your time series could be things like suddenly out of nowhere there might be a peak here because of some event occur. Maybe electrical load, some example of electrical load, right? So you have a higher electrical load on the weekend, for example. So the weekend, when the day of the week for the weekend like pops up, that could represent the event occurrence. The fourth one, this is the what we call future regressors. Whatever variable that you can compute its value at the future times, it is called the future regressors. In our application, this is clear sky irradiance, weather forecast, all of that. Auto lag. This is what we call by the auto regression. So if this is YT, so these explain the dynamics from YT minus 1, YT minus 2. So in NeuralProphet, what they did is uh, to have fully connected neural network where you apply the lag of YT as at the input layers. Okay. Next component, the last module. This is called uh, eh, oh, this is called the lag, exogenous lag, or LT. Uh, Same idea, right? So use fully connected layers, but the input would be the lag of exogenous variable. Example of lag exogenous variable in our application would be something, for example, the cloud. Okay, the cloud you can construct from a satellite is exogenous because the variable cloud is not irradiant, something not irradiant, and because you can only compute it in a historical sense, so that's why it becomes the lag exogenous variable. So in the NeuralProphet, the code is very simple. You prepare the data set and you determine, you set the number of forecast steps and the number of lags in each module. Hmm. Um, uh, hmm. Next, let me give some overview about machine learning algorithm that is very effective, very efficient. Regression tree. So when we have a tree, so this is an example of your features. In this picture, the feature is in two-dimensional. And suppose these are the data set, right? And that lies on the R2 plane. Okay. So a regression tree consists of a splitting rules. So suppose you have x like x1 and x2. X1 is a feature. So it has a splitting rule. For example, whenever your x1 is less than a threshold, go to this direction. And when you have hmm, let me so this is called a leaf or the terminal nodes. These are the values of your uh these going to correspond to the value of your response y. So the regression, how it works, that you're gonna partition the feature space into according to the splitting rule. For example, when x1 uh is greater than 4.5, so you come this way, and then you see another splitting rules again. Now let's consider x2. You split this way, you split that way. Okay. Um when so this position is called internal nodes, and this is called branches. So whenever you apply the let me like see some example again. In this example, you have two features. You have like different partitions. So in the terminal node or the leaves, it gives you the region. All right. For example, it gives you the regions in this way, R1 or R2, right? And this region is gonna contain some data point, some data point, some data point, right? Some data point. Mhm. The way it works is that based on the feature values, based on the features value, and according to the to the splitting rule, you will end up at some region. You will end up at some terminal node, right? The rule is that, okay, so this is the data set that correspond to x and y, right? So the decision tree will take the mean of the y that falls into this region. Okay, that's how you make a prediction when you use the tree. But now the question is, how do we know that we gonna use these splitting rules? So when you train a decision tree, is it is to determine this threshold, or basically how to like make a partition of your feature space. Okay, so in a regression tree, we will use the term region one. For example, region one, it's associated with the feature xj and a given threshold. For region 2, for example, for region 2, it also explained by a threshold S. So um, so when you train the tree is to determine how to split into different region so that the so that the sum square is minimized. So this is the actual I, and this is the y hat. This is the y hat that you obtain as the mean of all samples of y in the terminal node. Hmm. Okay. So this is like a general idea. Um, when you this is how you develop a tree, right? Um, how you develop a tree. Now, we can apply ensemble techniques on decision trees. One of them that is very common is to use the technique of bagging. The technique of bagging is that we bootstrap samples. We bootstrap sample mean we draw. Suppose we have like this data set, right? We only draw only some of them, all right? And we use the bootstrap samples to train the submodels or what we call the learners. Suppose we have B bootstrap samples, like each one may not be the same, right? And then we get B decision trees. Backing is to take the average of those learners. Okay. So the reason why we apply the backing technique is that each decision tree typically suffer from high variance. That's one issues in the tree. So when you do the average, this is what because this is what we get from bagging. So recall that when you have suppose you have like n quantities that each of them may have a variance of sigma square. Recall one property in statistics is that when you take the sample mean of n entities, the variance of the sample mean will be deducted by a factor of 1 over n, right? So that's why we hope that by making the average or do the backing, we can reduce the variance of each learners or each decision trees. Random forest, random forest or RF model um, is an ensemble technique that relies on the backing technique. Okay. So suppose you have x1, x2, x3, xp as the features for your tree models. Okay. The random forest will randomly pick only a subset of predictors that can be determined by the choice of the user. I think it's the parameter max feature or something, right? You can give the ratio, or maybe you can say, if I have p features, I will use only square root p features. Okay. So once you pick only the subset of features, you're gonna train a submodel or a learner. So suppose you like out of P, you pick M predictors, all right? And then you train one model. And there's also a choice that you can say that, oh, I'm gonna bootstrap the sample as well, all right? And then what you do is that you're gonna average all the predictions. You're gonna make the sample mean of the of the decision from each trees, and the way you do that is to decorrelate the trees, because we hope that by choosing different subsets of the predictors, your learners are now decorrelated. Mhm. Uh, so this is what I note here. All right. So making the average of the tree becomes becomes more reliable. Mhm. Um, Based on the decision tree techniques, there is also model called LightGBM developed by Microsoft, Light Gradient Boosting Machine. So it has a broad concept that can be explained as follow. So typically, when the tree grows, it grows level-wise from one node to the next level. It grows these two nodes together. On the other hand, for the light GBM, it is called leaf-wise tree growth. So when you go from here to here, you decide which node you would split, all right, and you pick only that direction. So you're gonna choose the way to grow the tree by choosing the leaf with the maximum delta loss. It basically to tell you that if I go to that direction, my loss function have uh, will have a maximum improvement. All right. And when you get here, right, you have to decide. Uh, you don't grow all of them, but you pick this one because that direction again has the maximum delta loss. And also it has an improvement in computational uh, techniques. It utilizes gradient-based one-size sampling and exclusive feature bundling. Basically, it makes the algorithm run faster when you train the LightGBM. So I have only this comment. We will see the code in the next video. Um, Support vector machine is one of the classical machine learning techniques that we use. Um, Support vector machine can be implemented for classification and regression. So for SVM that used for regression is called SVR, support vector regression. So the way it works is that it try to decide the hyperplane W, the normal of the hyperplane, and the translation term. Okay, whether it's this direction, that direction, this direction, and it tries to so this hyperplane that looks like a tube, right? And it has this width, all right? So this width is to specify the epsilon in sensitive loss. So it basically means that whenever the residual is this small, you don't have the penalty, and then the penalty grows as the residual grows larger. So so you try to capture with the prediction, but you allow to have a certain degree of the residual specified by this. Mm. Um, to since the SVR model has the output as the scalar, so when we apply for multi-step forecasting, you need to break down. Uh, you have to implement multiple SVR models. Okay. Um, I forgot to comment that the tree-based model, random forest, and LightGBM also has a scalar output. So when you want to forecast with the multi-step, you need to train multiple tree models as well. Here I would like to make some comments about solar forecasting techniques in literature. So, uh, uh, the literature follow the literature of wind power forecasting. So previously we have the physical methods. Physical methods like numerical weather prediction. Statistical methods include the time series, the linear regression, nonlinear regression, and now it becomes to the era of machine learning. People use neural network, SVR, wavelet k-mean, all of that, all right? Self-organizing map, the fuzzy logic. And now we're in the era of deep learning models. So we have as of now 2025, right? We have CNN. As you all know, we have recurrent neural network, we have LSTM, we have GRU, we have transformer, we have GANs, and many more. I think so that's why I haven't got the like a full literature yet on the deep learning model, because the literature on this grows very fast. But they are already out there as of now, 2025. So last, I would like to make some comments about all of these techniques. We can take a look at them, um, and maybe we can conceptually consider that they are, I mean, each of them is either one of the three categories. Okay, the first one, okay, um, hmm, okay. So the model, okay, if I broadly categorize, I would say the model is either single output or the multi output. Okay. So in this configuration, okay, your my model handle the multi output. Okay. My model is static. My model is static because it means that the model description is a static description. It doesn't contain temporal dynamical model relationship between input and output. So when I have this static model, but I want to represent temporal dynamics, I will have to put the lag information of my response as the input. Okay, so this is an example of exogenous lag input. So this is type A. Who is an example of this type? ANN. Okay, ANN. Uh, NeuralProphet is one of them as well, because neural network for the auto regression and lag regression modules, they use this as the as ANN. Next one. The model is single input and static. Okay. So when I apply the technique that release a single input, but my original forecasting problem have to release multi-step forecast, I need to train edge submodels. So suppose my edge is the horizon, right? So I have to come up with a feature set that consists of auto lag and exogenous lags, and then apply those input. Remember that all of the submodel has one thing in common, is that whatever input that you put here is only the recent input up to time t, because the time t is the time you perform the forecasting. Example of these of the model in type B are tree-based model, random forest, SVR, right? It release scalar output so that you have to train multiple models, and the trees model are static. So that's why you have to put lag information as the input. The last type is a very complex one. The last type, first, it released multiple input, multi output, or the target vector. This model is a dynamical model. It must contain some input output relationship as dynamical equations. So this example One example of this type is LSTM that we just saw previously, or any recurrent neural network would also in this type. Um, how long is this? How long has it been? Mm-hmm. Okay. Next. People have applied many machine learning techniques, and they come up with a way to, like use many submodels as an interconnected system. So here I'm going to explain the extensions of applying the forecasting models. One extension is to have adaptive model. This idea is very simple. So usually you train the model offline, right? And you train the model and you use it. So in this framework, it means that your model parameter your the model parameter can be retrained, can be adapted online using the new information. Okay, so people have used this with the linear regression before. The keywords is recursive least square, the Kalman filter, or the MOLS, or light estimation. So this is classical estimation theory. Okay, and I think for uh, with the context uh, of the recent days like this, it means that your machine learning models can be retrained on the fly as you have more and new data arrive to your system. The next scheme that I would like to mention is parallel models. It parallel models according to weather classification. So suppose you can do unsupervised learning to classify the data into each type, sunny, cloudy, rainy, something like this. And you can, because of each weather type, you have assumption that maybe the forecasting model should be different, should be trained with different set of feature with different architectures. So you may have sunny model, cloudy model, rainy model. And the way to deploy it is that first, the weather information arrives, and based on the weather classification principle, the mechanism that you can use k-mean, self-organizing map, or SVM. And to select one of these, right? If it goes to this, you apply the rainy model. Sometimes people distribute as a parallel models according to the time split. So that means that they don't take they don't exploit the temporal dynamics of your time series. So they just split the model, for example, the model to forecast for 6 a.m., for 7 a.m., and so on. So you're gonna have many submodels here responsible for each time of the forecast. Mhm. So we have some example that at our department as well, that we have model for early morning, because for early morning the area irradiance is very small and typically follow the trend of the clear sky model. That's why by this assumption we just pick solar zenith angle and the clear sky as the main feature, and we use only the recent values of the measurement INP to predict the power. Okay. The same principle apply for the evening, because in the evening typically the irradiance follow the trend and it has small values. On the other hand, the reason why we split the model for midday is because from during the midday, the irradiance fluctuates a lot. These are typically the duration that is very challenging to forecast. So that's why during this time we use more complicated features. We use many lag orders in INP, and as well as the future regressors. Mhm. Um, Cascade model. It based on the assumption that Using one model maybe is too simple to learn the whole nonlinear dynamics. All right. Why don't we first apply the first model? All right. So suppose the first model has the output of Z, right? For example, this is solar irradiance from the weather forecast. And then you apply the second model to compensate whatever remaining dynamic that has been unlearned, that hasn't been learned yet. So you can apply the machine learning techniques here using more feature, more information like clear sky, power, solar power, sky condition. So the way you interconnect between these two models is sequential. So that's why this is a type of cascade model. Bias correction. Bias correction means that um, it based on this structure that your y depends on the prediction from the first model, but that still has a remaining residual. Okay. So these residuals still maybe still contain some dynamics of Y that cannot be learned by the first model. Mm. So you construct the second model F2, okay, with some feature Z, okay, and use E as the input. These first residual. So you try to correct to predict a more like an improved residual. So E hat is the predicted residual. And then you feed it back to the Y1 hat, and you hope that this E hat will adjust the output from the first model for the better forecast. So this is called bias correction by this mechanism. So in the diagram, it follows like this. Okay, your first feature goes to model one, example, the numerical weather prediction model or some time series model, something that you assume that, okay, the quality of the forecast may not be, uh, maybe the quality is limited, all right? So you get Y1 hat. Mhm. So for so to get Y1 hat, and then you compute the bias. You compute the bias. The bias is to, of course, how can you get the bias? You must compare this predicted with the true value, right? But at the moment t, you will not have the uh, at the moment you will not have the ground truth value. So that's why when you construct the bias, this is the old bias. So you have the delay step here. This is to compare with the measurement value in the past, and then you get the bias. So the bias will become the input for your second proposed model. This can be another machine learning with some other exogenous input. All right, and you get the predicted bias E hat, and then you feed it back to your first forecast, and then get the better forecast here. Mhm. So this is called bias correction. Use the second model to learn dynamic of from the residual error of the first model. Mhm. Okay. Aside from this, I would like to mention that the proposed architecture can be many more, all right? And because, as I said, the literature on this is huge. People keep proposing new techniques all the times. So I will prepare this material in the next lecture in um, so next I will keep it in the next video. How to evaluate the performance is not trivial. There should be some guideline. But next in the I mean uh I think you can see everything from the first to the end. Like, oh, this is a method we use to learn how to calculate, and we show you by example. And we keep the contents of illustrating the coding example till the end because that's gonna be too detailed. All right.